Okay, today we will cover Chapter 10, Parametric Equations and Polar Coordinate. Section 10.1, Polar Coordinate. Okay, in this chapter, we deal with two new ways of describing a plane curve. One is a parametric representation, and the other one is the polar coordinate representation. Those will be very useful to represent the variables x and y in terms of the third variable t, called a parameter. Okay, the polar coordinate system is another convenient way of describing a curve. So we also look at derivatives, arc length, area, and curve sketching in parametric and polar coordinate system. Okay, first, section 10.1, parametric equations. As you see in figure 1, this curve C cannot be described by a function y is equal to f of x because it has two values. At one value x is equal to a. So, since x and y coordinate of the particle depend on time t, we may write x as a function of t and y as another function of t. Okay. So if f and g are continuous function of t on an interval t, then the set of ordered pairs f of t and g of t is called a plane curve C. The equation x is equal to f of t and y is equal to g of t are called parametric equation for the curve C. And t is called a parameter, as you see in this figure 1. First example asks us to sketch the plane curve defined by the parametric equations like this. X is equal to t minus 1, f of t, and y is equal to g of t, which is t squared minus 2t. And minus 2, t is between minus 2 and 4. Okay, this graph can be drawn in this way. Okay, this is example 1. Okay, so this is a function x is equal to t minus 1, y is equal to t squared minus 2t. Okay, if we draw the graph of that function of the parametric function in a parametric plot, in x-axis, y-axis, and t from minus 2 to 4, then you will see the graph looks like this. As time changes from minus 2 to 4, and that x-axis, x point and x coordinate value and y coordinate value changes like this from time minus 2 to time t is equal to 4, like this. It moves like this. Okay, so this because when time t is equal to minus 2 and x is equal to minus 3, y value is 8. When t is equal to 0, x value is minus 1, y value is 0. So when t is equal to 2, x value is 1, y value is 0. So this point. And when t is equal to 4, then x is 3 and y is 8. So it agrees with it. Okay. So for such a function, for parametric function, we can eliminate the parameter t from the both equation x and y by substitute so like this. T squared minus 2t can be written in this way. So x plus 1, so t minus 1 is x, so t is equal to x plus 1. So it can be written in this way. So y can be written as s squared minus 1, as you see in here. So this parametric function can be written as a function y is equal to f of x, like this, by substituting those t in terms of x and y. Okay. When t is in between a and b, the curve with parametric equation x and y has an initial point f of a and f g of a. So when t is equal, when a is starting point of t, then the corresponding point in xy plane, f of a and g of a, can be is called as the initial point, and this t f of b and g of b point is called the terminal point. Okay. 터미널 포인트는 볼드를 해주면 되겠죠? 문군. Okay. Example 2 is find the curve represented by the parametric equations. X is equal to cosine theta, y is equal to 3 sine theta, and theta is from 0 to 2 pi. You know, from here, cosine theta can be written as x over 2 and sine theta as y over 3. You know, cosine square theta plus sine square theta is equal to 1 for any theta. Okay. Okay, so since we know 1 is equal to cosine square theta plus sine square theta, and this can be written as this by substituting cosine theta and sine theta, then it can be written in this way: x square over 4 plus y square over 9 is equal to 1. Okay, this is a function for an ellipse whose center is 0 and 0, and whose vertices are 0, 3, and 0, minus 3, like as you see in here, like this. Okay, so this parametric equation can be written in terms of x and y, like this. Okay. Finding parametric equations for a graph. So the example says, find the set of parametric equations to represent the graph of y is equal to x squared minus 1 using the following parameters. Say, the first case is that t is equal to x. Okay. And the second, the slope m at the point x and y is dy over dx. Okay, anyway, first case, we can, since we are using the parameter t, whose value is just same as x, so we can just replace x by t on a function y is equal to f of x. So we can easily can be written as y is equal to t squared minus 1 for all t. But the second case, if we use this, if you rewrite this in terms of m, then what is this m? M is a slope. So slope is dy over dx. Okay. So dy dx can be found as 2x. So x can be written as m over 2. So this y equal x squared minus 1 can be written as m over 2 squared minus 1, which is this. So y can be written in terms of m in this way, this way. Okay. The next important example is a cycloid. Cycloid. You know this one. This can be, 이게 이제 자전거 바퀴가 이렇게 굴러가면, 자전거 바퀴가 처음에 원점 바닥에 시작한 것이 굴러가면 위쪽으로 올라갔다 또 내려오고, 그 다음 또 올라갔다 내려가고 해서 이런 모양이 되죠. Okay. Cycloid looks like this, as the wheel moves, wheel of a bicycle moves. The example 4 says, determine the curve traced by a point P on the circumferences of a circle of radius r rolling along the x-axis in the plane. One position of P is the origin, like this. So we may click okay, we may copy this web address. Okay, this cycloid can be drawn by this parametric equations. I will show you. Okay, here, if we choose x of t as this, x of t as a times t minus sine t, and y of t as a times 1 minus cosine t. Okay, then control V. Then we will see the graph like this. If we give a and give slope size, canvas size is small, then what is parameter t? A should be small enough, so to see exactly. Okay, and then canvas size is big enough. Okay, then you will see if we make the canvas size a little bigger, then we will have this. Okay, if we want to see how this graph was made, then I am generating the animation of the cycloid. Okay, so I'm drawing a graph when a is equal to 1, and in the interval from minus pi to 5 pi, like this. So this parametric graph, parametric function, the graph of this parametric function moves from when t is equal to minus 4 pi, it starts from here, and as t moves, it runs like this, as you know in a parametric cycloid. This cycloid can be made. Can be analyzed in this way. From here, the x is equal sine r times theta minus sine theta, y equal r times a minus cosine theta. So, for one rotation of the circle described by theta from 0 to 2 pi. From here, if we give a parameter from 0 to 2 pi, like this, then you will see we will have exactly one cycle of the cycloid. It's a periodic. Okay, yeah, you will see exactly a period. Okay, anyway, this cycloid this has been a very interesting and important subject to study. Long ago, from Galileo and Huygens and Bernoulli, and they all studied on this subject. Okay, so parametric function, parametric graph, it has very interesting properties to study. Okay, example 5. Sketch the curve x is equal to t cubed minus 1, y is equal to 2t, when t is from minus 2 to t. Okay, then copy this web address. So I will show you how that this is the example 5 okay, parameters. So x is defined as t cubed minus 1, y is 2t, and a from t from minus 2 to 2. So I do draw the parametric plot of this x and y point from t from a to b. Okay, then let's draw the graph. And this is a graph of that parametric function. So it starts from here when t is equal to 2 minus 2, and then moves in this direction to when it ended, and when x is equal to when t is equal to 2. Okay. So this is exactly the graph that I draw from here. Another thing, sketch the curve. X is equal to 2 cosine t minus cosine 2t, and y is equal to sine 2t minus 2 sine t, t from 0 to 2 pi. Then we can also draw the hot type graph by parametric plot, like this. X here, y here, and t from 0 to 2 pi. Okay. Similar things. Sketch the curve for t from 1 to 20, when x is equal to 12 sine cube t, y is equal to like this. Then we can draw this graph in this web address. This was done in here. Parametric graph. And in here, then you will see the graph that you have seen in here. The graph, like you see, x is a times sine t cube, and y is b cosine t minus 5 cosine 2t, and like this. Also, we can also see this animation from minus pi to pi, how this can be drawn. And also, so I'm making about 20-30 the images and making the animation out of it. It starts from here when t is equal to minus pi, and it ends at the same point when t is equal to pi. This graph can be saved in this way. We can copy here, and if we copy in the Word file, then you will have an animation in your homework solutions. So this is a very easy way of doing making the graph. We can make, if we change this interval from 0 to 2 pi, like this, then it starts from when t is equal to 0 and end it, and when t is equal to 2 pi. So yeah, you can make many different type of the images. In this case, it starts from 0 to 0, the origin, and moves like this. Yeah. Okay, anyway. And so, yeah, you can use those knowledge that we have been through to find the Cartesian equation of the curve, and draw the graph of these parametric functions. Before, I used this graph, these many graphs, to show one, when t is equal to 0 starts from here, and when t is equal to a certain point, it moves in this way. But eventually, I started to draw the image with the arrows to show it. All those move at once, like you see in here. Okay, so this is much easier to analyze it. So you can now, whatever function you have it, all you have to do is use the same parametric equation, plot parametric equation graph. Then you will have all those different things. Particularly in here, all you have to do is give in this web address, you give the function x of t in here and y of t in here, and change this, use these sliders, and you can change the range of t's and things to draw all different type of the graphs that you like to draw. So now, with this tool, Sage tool, that we developed, it will be much easier. Okay, any questions on parametric functions?